Hello, everyone. Welcome to today's Managing Multiple Water Temperatures online seminar. Today's presentation will be about an hour in length and is worth 1 PDH or Professional Development Hour credit. My name is Miranda Getling and I'm the Viessmann US Academy Manager. I just wanted to take this opportunity to say thank you for attending today and welcome you to today's seminar. And I also wanted to introduce you to your instructor today, who is Jody Samuel, and give a little glimpse into his experience for those that may not know him. Jody is a graduate of Maine Maritime Academy with a degree in marine engineering. Over the past 20 plus years, he has worked with various companies, including Amtrol, Viessmann, and Calefi, serving in various roles, including application engineer, product manager, training manager, and manager for engineering education. Currently, he serves as the Project Development Manager for Viessmann US. And before Jody begins, I do have a few housekeeping items to go over with you. And as I stated in the beginning, this is worth 1 PDH credit, and RCP is the provider we do this through, and they do require those that would like this credit to fill out a survey. So you will get that survey by the end of the day today. And once you fill out that survey, we will send out the certificates via email within 5 to 7 business days. When you registered for the seminar, there was a section regarding if you wanted this credit. My email will be on the last slide of the presentation today. Feel free to email me if you want to double check if you selected yes or not on that registration form. Everyone will stay muted throughout the entire seminar. However, at the bottom of your screen, you should see a Q&A button. On the left is the desktop laptop version, and on the right is that mobile device version. You can type in any questions you have in here. Jody will be stopping about halfway through and at the end of the presentation to answer any questions submitted. And then we will follow up this seminar with a Q&A document of all of the questions asked in this section and the other session that we had on the same topic, and make sure that you get all of the answers that have been answered by Jody. We are recording today's seminar, and it will be posted on the US Academy page, which is viessmann-usacademy.com. And once you're on that page, you can simply click into our video library, which is located on the top of the header. Or if you scroll down, we have the larger video library section, which you can simply click into. Once you're in that video library, this is what you will see. And at the top is that search function. So you can simply type in managing multiple water temperatures, and the seminar will populate. Or we do have that recorded online seminars section, which is where this recording will lie, as well as all of our previous online seminars that we have had so far. Since this is a collaboration between the US and Canada, we will also have this on our YouTube channel, Viessmann North America. So if you go to youtube.com and type in Viessmann North America, our page will populate, and then you can go to the video section or the playlist to see this seminar and all of our other videos we have as well. And with that being said, let's begin. Here is Jody Samuel.
As Miranda said, welcome to the presentation. Today we're going to talk about managing multiple water temperatures. And as with a lot of these discussions, with my position at Viessmann over the years, a lot of these presentations always tend to start out as a phone conversation or two with somebody, and they end up being a presentation. And the same thing with this one here. So a couple of housekeeping slides first. Miranda already talked about this, so I'll skip over it. The presentation is copyrighted. If you would like a copy of it, when you fill out the survey, just make a note in there and Miranda will provide you with a PDF version of it. I'm going to jump over the statement of purpose and kind of move into the learning objectives. And today's really all about projects that need multiple water temperatures. So when we complete this presentation, you should be able to list the conditions that lead to multiple water temperatures in a hydronic system, and they are varied. Describe the methods for providing multiple water temperatures, including multiple boiler set points, motorized or electric mixing valves, thermostatic mixing valves, injection pumping. They tend to be the primary methodologies. So that's what we're going to talk about. We'll discuss how to determine how many water temperatures are needed for a hydronic system. And then finally, we're also going to describe the methodology providing a constant temperature to a heat pump loop. When we start to get into the topic, this is one of these topics that always tended to be, if you will, an orphan out there. And this seemed like a good place to add it in there because this topic leads into it quite well. Okay. Now, when we talk about buildings and we talk about the need for multiple temperatures, it really is all about what we're doing with the water that the boiler is producing. There's in the space heating world, we have high temperature, we have medium temperature, we have low temperature applications. Also among them, there are sometimes high temperature applications that are fixed points, doing a spool or a pool or spa heating, doing domestic hot water. And the thing is, when we start to look at the application, we start to look at high, medium, and low temperature. It's not just about the temperature, but it's also about controlling that temperature. And for space heating, it's always the overlay of adding in outdoor reset control. So we may have something that's considered to be a high temperature application, and that high temperature on the design day, may take a very high water temperature. We may have something in the medium temperature side of things, medium temperature, probably about 120 to 150, somewhere in that neighborhood, where the temperature is not as high, but we also still want to do outdoor reset, or we may have low temperature type applications. So when we start to look at the need for multiple water temperatures, the requirement behind that can be quite varied depending on the type of heat release in the buildings. There's baseboard, there's fan coil units that require higher temperature. Fan coils could be high temperature, they could be medium temperature, the same with baseboard and different type of radiation. And then you also have the low temperature, high mass radiant is the one that everybody thinks of. So when we start to look at selecting the right water temperature and selecting the correct or the proper heating curve, a lot of times there's not a single solution for the building, because you'll get into that building and all of a sudden there's a mixture of different types of radiation, different types of heat emitters. So for instance, from our example, you might have a building that has 3 different types of heat emitters: baseboard, cast iron, or and then concrete poured over radiant. So you may have a high temperature, a medium temperature, and a low temperature all in the same building. It actually happens quite often. We'll have applications where they don't put radiant through the entire building. They may do certain areas that are radiant. Certain places in the building, here we show baseboard, but part of the building may have hydro air in it that requires a much higher temperature. And so all of a sudden, you often have these mixed heat emitters. An existing building that they're adding an addition on. The existing building has high temperature for the baseboard that's in the building. The new part of the building has radiant. So a lot of times we'll run up to the applications where there's a need for multiple water temperatures. And the key with needing all these multiple water temperatures is somebody's got to figure out the best way, and from a cost standpoint and from an operational standpoint and from complexity, what's the best way to meet the requirements for all of these water temperatures? And even to the fact when we start to do, somebody will say, well, it's got to be simple. I'm going to do radiant through the entire house. It may not be, depending on the methodology that's used for the radiant heating, above floor, dry system below floor, large mass concrete slab systems, floor coverings, floor types. There actually may be the requirement for multiple water temperatures within a radiantly heated building. So we start to look at the overall requirement in some, if not all jobs. There is a lot of times the requirement for managing multiple types of water temperatures because of the heat emitters in that building. And also, well, I'm going to throw it in here, it'll come up again. Also, domestic hot water works into that discussion as well. Now, the one thing when we start to look at doing multiple water temperatures, it's not just about the water temperatures, as I started out earlier talking about for space heating. So I may have the requirement, say, for 3 temperatures here, temperature 1, 2, and 3, which really mean heating curves for outdoor reset. That may be all space temperature. But also when I start to look at managing my multiple water temperatures, I may have domestic hot water as part of my boiler plant. So I have to manage the domestic hot water temperature. And while I'm managing the domestic hot water temperature, I have to still manage the temperatures going out to the system as well. I'm not showing here, but I may also have an external demand. Think snow melting or pool heating or something along that line. That becomes another temperature that I have to manage as well. And with a commercial building, we might as well throw in the building management system. There may be temperatures coming in through a 0 to 10 volt signal to change set point, as well as electronically through the building management system, in most cases through a gateway. So when we start to look at managing multiple water temperatures, there's a lot of information that can go into the boiler system to try and drive things. But the key is when I start to stack all of these against each other, there has to be a methodology to meet the best combination of control and complexity to drive the water temperatures that are needed to adequately heat and keep that building comfortable. Now, the first thing that happens when we start to look at doing water temperatures really is the question about how many temperatures does a project really require? Yeah. Now, often we'll run, as I said earlier, often we'll run across projects that people will require multiple water temperatures. One project that I was involved in probably about a dozen years ago, the project came across and the requirement came out, we need 8 water temperatures. So, based on the structure, based on the floor material, the coverings, the type of heat emitter that they're using, sometimes you'll run across projects where 3, 4, 5, 6, in that case, 8 water temperatures may be called out on the plan to adequately heat the building. Now, the one thing when I start to look at these projects that you start to get into the higher number of water temperatures, the question always comes up is, do I really need them all? Because right here, usually when we look at control in the building, I usually see probably 2 levels of control. There's the control level that takes care of managing and controlling the water temperatures, but there's also some level of zoning through the building. Something sensing the temperature in the spaces themselves, and then controlling flow to the various parts of the building to maintain a comfort level in the building itself. So if I have that level of zoning throughout the building, a lot of times I can come out and take another look at all the water temperatures, these 4, 5, 6, 8 water temperatures that are called for, and really try and decide on how many really are needed. So as an example, let's say I have a project and we're thinking that project needs, and I'm going to show here 5 different water temperatures to take care of the building. I'm just going to highlight 3 of them. Let's say we're going to talk about our different methodologies, but I'm going to say this part of the building needs 130 degrees Fahrenheit. That part of the building needs 125 degrees Fahrenheit, and that part of the building needs 120. 3 distinct water temperatures. And from a design standpoint, if this is the right water temperature, when the design temperature outside is happening and I provide it with 130 degree water, this is constant circulation here. 125, constant circulation here. 120, constant circulation here. But from an aspect of operation and comfort, if I start to add in a certain level of zoning or control, I can provide a little bit warmer water temperature to a part of the building and still maintain comfort. But what I'm going to do is I'm going to back off from the concept of constant circulation and start to move into intermittent circulation. Namely, and I'm going to come to my rule of thumb right down here on the bottom, and you'll say, talking to people, you may find that these numbers change. But if I'm looking at multiple water temperatures, and those water temperatures are within about 10 to 15 degrees of each other, they can be combined and called a single water temperature. And that water temperature is the highest of that grouping. And so we set up with control on that water temperature and then let zoning go to the other areas of the building and then have intermittent operation. So rather than having 3 mixing valves or 5 mixing valves, let's just put a single mixing valve, and let's say 130 degrees was the highest water temperature. So right here, here's my 130 area, here's my 125, here's my 120 area of the building. So I control and I maintain water temperature here to 130. If this part of the building was requiring 130 degree water temperature, this control valve is open for 100% of the time. That part of the building is running in constant circulation, okay? Now, this part of the building was designed for 125. So my water temperature is going up about 5 degrees hotter than what I need based on my design of the building, okay? Now, it's gonna put, because the water's hotter, the heat emitters are gonna put out a little bit more energy than at 125 degrees. So what's gonna happen here is I'm gonna maintain that water temperature, but now the thermostat in your control valve now will take over. This control valve right here may only be open about 90% of the time, 90 to maybe 92. But again, through the control valve itself, we're still going to maintain comfort in the building. Same thing happens over here where I need 120 degree water. I need 120, but I'm getting 130. The valve will control to maintain comfort in the building, but still, I'm still at about 85% of the time with 85% circulation. So although I call it intermittent, if we keep the temperature band close enough, we still have a high level of demand on the system where we are circulating for a large period of the time. And by doing this, we've simplified the install, but really have not lost anything from a comfort standpoint. So again, when we look at doing multiple temperatures, it really is, let's see what we have for temperatures. And then if we can group these temperatures together, let's get this down to a much more manageable control package to deliver those water temperatures. As a reference, the building that I was talking about from about a dozen years ago, that from a design standpoint, they said they needed 8 water temperatures. We ended up servicing it with 2 mixing valves. So it really needed 2 temperatures once we started to group those water temperatures together. So the first thing to do is to actually determine the amount of water temperatures you need. So once I have that, I say, okay, these are the distinct water temperatures. Now the question becomes, how do I deliver them? Now, the simplest approach is, again, a lot of this is is dependent on the level of zoning, but the simplest approach when we start to approach these is really, is there a way that I can change the boiler set point? So rather than adding extra devices to drop the water temperature, let's simply manipulate the set point of the boiler. So what that really means is, from a boiler standpoint, we don't have one control input into the boiler. We need multiple, 2, 3, 4 control points coming in. So the boiler can recognize when these demands are coming in, and then each one of these demands either has to be associated with a pump or it has to be associated with a valve. So one approach for this, and this is, by the way, this is not the approach that we take, is I'm going to call it prioritized load. And it's utilized by a couple of other boiler manufacturers out there on their residential boilers. Now, in this prioritized load, all loads are not serviced simultaneously. They're actually sequenced, and that sequencing is based on what's called, they call a priority value. So each one of these loads is assigned a priority value, and that priority value determines the preference of which one occurs, and how long, from a weighted average standpoint, how much time is devoted to each one of those areas. So basically, the higher the priority value, the longer the runtime. Okay. Now, the challenge with doing this is, if you look at these water temperatures, generally when somebody looks at doing a water temperature for a portion of the building, so for instance, 130 degrees in this part of the building, 150 in this part, 170 in this part, those temperatures are really based on a heat load. And from an aspect of that heat load, it's all about this flow of heat from the combustion process to the outside air. So here I have the wall of the building. Let's say my outside temperature is 0 degrees. And what I'm really focusing on is the water temperature here. Based on that delta T between across this wall here, there's going to be a certain amount of heat loss that occurs if I have a 70-degree room and a 0-degree temperature outdoors. With that 70-degree room and that heat loss, I know that my baseboard or my heating element or heat emitter in the building has to put the right amount of energy into the living space to balance with the outside. Okay, so I choose a water flow rate and I choose a water temperature, assuming that I'm going to put heat into that room 60 minutes out of every hour. So what happens is if everything is chosen right, 180-degree water at design flow rate will put the right amount of heat into that building on a per hour basis to balance with the amount of heat that's coming out of that building also on a per hour basis. Now, the challenge with this prioritized methodology of multiple water temperatures, this process assumes that I am flowing at 60 minutes every hour. If I start to cut back where all of a sudden it's only flowing for half of that time period, I may not be putting enough heat into the living space to balance to the outside. So for me, this always becomes the big discussion when somebody utilizes this type of control. And it kind of comes up as well when you look at their manuals on this this approach to doing water temperatures. If the load is under service, the target temperature, the temperature target can be increased. So basically, somebody calculated that you need 170-degree water to heat this area of the building based on a specific flow rate. If it's not keeping up under priority load, bump that number up. Make the heat emitter start, that way there the heat emitter can put out more heat. Problem is if I start to bring the temperatures up, my return water temperatures come up as well, and my boiler may not be as efficient as it can be. But this is a methodology out here, and it does come up in discussion when somebody talks about multiple water temperatures and they say, well, what about this methodology? This is what they're trying to achieve, but the problem is the concern always becomes underserving the loads based on that priority value. So the other approach, and I'm going to call this competing loads because I really have not found a good term for it, is let's service all the loads simultaneously. Okay. And what we're really coming down to is let's compare all the loads in the building and select the highest temperature to service all the loads that are calling. And for this to work, though, you do have to ensure that the building has adequate zoning to prevent any part of the building from overheating if it is receiving a higher water temperature than what's needed. So very similar to the other approach, I have multiple sensors throughout the building, thermostats. All of them come back to the boiler. Each one of these are now associated with a water temperature. And then the system will control multiple pumps, in this instance, through those areas of the building. So let's say this part of the building requires 150-degree water. This part of the building requires 160-degree water. This part of the building requires 180-degree water. So all of that gets set up and it all gets programmed. And again, you bring it in, everything comes in here so that the building knows which area, the boiler knows which area of the building is calling. And from the aspect of the operation, it simply looks at it and says, okay, I look at my loads, I look at what's calling, and then I will always default to the highest load of the bunch. Okay, so it's serviced simultaneously. It compares the multiple temperatures and it selects the highest temperature to service all loads. The zoning throughout the building prevents overheating because there are situations where parts of the building will be getting water temperature that is too high. And the other one is it's only practical from this aspect without any additional equipment if there's no high temperature limits on any of the areas of the building. What always comes up as a concern is if, say, somebody does an underfloor radiant and they're trying to do it this way here, the water temperature that's under the radiant. Okay. Now, why this is better than doing just saying, okay, I'm just going to run it off of a single temperature. This from an efficiency standpoint is much better because if the load that requires the highest water temperature isn't calling, the system will select a lower water temperature, kind of like this. So I have these 3 circuits, all with their associated water heaters. Okay. Now, let's call this circuit 1, circuit 2, and circuit 3. Circuit 1 requires 130. Circuit 2 requires 150. Circuit 3 requires 170. If only circuit 1 is requiring, the water temperature is only going out at 130. and the water that's making its way back to the boiler, which the efficiency of the boiler is dependent on, is based on 130 minus the delta T. Okay. If everything always was tied to the highest water temperature, when this is going out at 170, it may only be coming back at 140 or 150, high enough that the condensing boiler wouldn't condense. So, under these conditions, if only this is calling, it's 130. If any combination with circuit 3 happens, then the boiler goes up to 170. But it always seeks the lowest temperature based on just what is calling. And what that will do is it will help drive the return water temperature down as low as it possibly can be to drive the efficiency. One other note on this, right here I'm talking about numbers. My expectation is this also is running off of outdoor reset control, and these are the design state temperatures. So on a lot of days, the supply and water temperatures are going to be lower than this to drive the efficiency. But with the simultaneous load, it always does a comparison and then picks the highest load of the bunch to service. Okay. Now, those are the two methodologies that we can approach it from if everything in the system can work off of the same highest temperature. Okay. If the approach is to deliver more than one temperature concurrently, then we now have to design into the system the equipment to drive the water temperatures for multiple water temperatures, for simultaneous multiple water temperatures. And generally, the approach is going to be through one of these three methodologies. It's going to be, could be an approach through injection pumping, or it could be that we approach it through using thermostatic mixing valves, or we can approach it doing motorized or electrical mixing valves. We'll talk about all three. All three of them have their place in the industry, but we'll talk about where, what each one of these represents from an aspect of multiple water temperatures. So the first one we're going to start is right on the top with injection pumping. So when we talk about injection pumping, and this happens to be out of a drawing from one of the Caleffi Hydronics. You can see Garcia Caleffi on the bottom here. So this is an older drawing from Bell and Gossett. So when we talk about injection pumping, what we're really talking about is having two loops here. So right here is the boiler loop. Out here this is the system loop or the secondary loop. And then between them, you're going to have a pair of pipes. And why it's called injection pumping is the pump will inject water from the boiler loop into the system loop. And then there's a second line over here so that as boiler water is coming across, system water is coming back on the other side. And by doing this, it allows us to mix water out here in that secondary loop, mix hot water from the boiler loop in with the cooler return water to maintain this lower water temperature in this loop out here. Okay. So when we talk about injection pumping, it's all about this arrangement right here, injecting the water from one loop into a second loop. Okay. So the details of this, as we said earlier, is we're going to inject it. And in order to maintain temperature, we want this to be variable speed. So we want to be able to use this to meter the amount of water that's being brought across from the boiler loop into the distribution loop. Additionally, we also want to have a methodology of balancing. So there has to be some sort of balancing valve in there that has to be set to set the proper flow rate when this injection pump is operating. So a couple of things that has to be considered in here in this design. Now, if I throw this into a boiler design, system design, this happens to show a non-condensing boiler. So what you'll have here is, now here's this loop design. So here is my distribution system. Here's my boiler system. And here is my injection system, making that crossover from the higher temperature boiler water into the lower temperature distribution water. And again, hot water comes across, it mixes with the return water. And by having that mixing, it will give me the right water temperature as sensed in the distribution loop. So that comes back into the control to control this. And again, there's a metering or a balancing valve in here that has to be set so that that pump will have something to work against and be able to give me the proper flow and give me the proper flow range to make this work. If we apply it to a condensing boiler, so here's my low loss header, and now I'm showing it with 3 different water temperatures. So here's my 3 injection pumps, here's my 3 distribution loops, and that allows me to maintain 3 distinct water temperatures with this injection pumping system. Okay, so it is a popular methodology of generating a lower temperature or multiple water temperatures simultaneous for the systems. Okay, so a couple of things with this. For this to work, first off, this has to be a variable speed. So that means that really it has to have a VFD, a variable frequency drive, if it's a conventional motor, in order to vary the speed of this injection pump. You know, or it could be an ECM pump, and a lot of times you'll see an ECM pump maybe with a 0 to 10 volt signal. The one concern with this always is the turn down range. Yeah, from 100%, how far can I bring it down? Can I bring it down to 50% of full speed or full flow? 50%, 30%, 25%. Yeah, and a lot of times when we start to look at these kind of concepts, you can't go down to a very small flow rate because of some sort of limitation in the way they're controlling the pump. Also, there has to be a balancing valve in here. And by having that balancing valve, that means that's one other thing that has to be set properly on commissioning to get that system to work. Additionally, depending on how they're designing it, when I start to look at from a pump standpoint, I am going to have to be able to move water through the boiler loop. I am going to have to move water through the distribution loop, and I am going to have this pump in between to move the water through the injection system as well. So a lot of times we're looking at a system that we may have 3 pumps, at least 2, maybe 3 pumps doing the work that we probably could do with a single pump, which means more electrical load. Okay. The other thing also, when we look at it versus some of the other methodologies, you know, there does have to be a control system to operate this variable speed injection system. And with this, that variable speed injection pump, the expectation is it runs continuously. So when you start to look at from an electrical load inversion, if you look at a thermostatic mixing valve uses 0 electricity. Or if I go with a motorized or an electric mixing valve, generally it's going to be a floating action. It's only powered when you have to actually physically move the valve, which happens just periodically. So these are some of the concerns when we start to look at doing an injection pump system. Okay. Our next option is doing mixing. Okay. And the first method of mixing we're going to talk about is doing a thermostatic mixing valve. So here's a typical thermostatic mixing valve. So it has a hot port. You can see it by the red dot here. A cold port with the blue dot, and then the mix off the bottom. Now these are non-electric, so there is no electrical and no control associated with it. And it provides a fixed mix set point. So it's a setting on the top of it. So, you know, when you do this, you end up with a fixed set point for the water temperature. This probably is your lowest cost solution compared to going injection pumping or a thermostatic approach. Okay, so how this thermostatic mixing valve works is you have a thermostatic element or motor inside here. The hot water comes in, the cold water comes in as well. And as the temperature in the mixing valve changes, the element inside there either heats up or cools down, expands or contracts, if you will. And that is what causes the mixing valve to change the mix between the hot and the cold. Okay. So it's a very simplistic system, works without power, does not communicate with the boiler. Again, low cost alternative for doing a mixed water temperature. From an installation standpoint, it's very simple to install. Here's our mixing valve here, providing for this load over here. So there's a hot water connection that comes in. I have a cold water connection that's piped in, and then I have a mixed on the outlet of it as well. The pump goes downstream of the mixing valve to provide flow through this loop. And as we said earlier, there's no electrical connection. So it's a straight mechanical device. From a design standpoint, I can integrate it into a multiple temperature system. So here's the drawing showing a typical multiple temperature system. Here's high temperature, 180 degrees, going up to this air handler. And I want to have 122 degrees going out to this radiant system. So the boiler is programmed to provide this 180 degree water temperature, running it off of outdoor reset control. And then I simply make a setting change on the valve here to get an outlet temperature of 122. Okay. So it allows me in a low cost installation to add this in here, get that required water temperature out to the low temperature application while I'm still providing high temperature to the high temperature part of my system. So it allows me to do that multiple temperature system. Okay. Now, the one thing with this is at a set point. So I'm going to say, as long as the temperature here is above 122 degrees, we'll get 122 degrees out of here. So it's not doing outdoor reset. However, you get, I'm going to call it a pseudo outdoor reset if the outdoor reset on the boiler and the distribution dips down below that temperature. As an example. So got my drawing down here, okay? So let's say that from our previous example, you notice I brought the drawing forward with us. So right here, I have a high temperature situation. On the design day, I need about 180 degree water. That's going to be about a heating curve of 1.6 on a -4 degree day. Okay. So this is the heating curve by which the boiler is operating off of. Now, additionally, I have my mixing valve out here. And that mixing valve has a set point of 122 degrees. So as long as the water temperature comes into that mixing valve, it maintains. So when the water temperature is 180 coming into the mixing valve, it gives me 122. If the temperature coming into the mixing valve is 158, I still get 122. But when the outside temperature is about 43 degrees, the heating curve right here is at 122. So at that point, the mixing valve is fully open. Okay, it's not trying to mix. Now, one thing I do have to add, I was actually, as I was working on this, ended up calling Cody Mack over at Calefi. He's one of their trainers over there, and I want to talk to him about a couple of things about mixing valve. One of the things that he wanted to remind everybody is in a thermostatic mixing valve, the ports don't have positive shutoff. So although I talk about it following here, there still is a little bit of mixing that occurs. So although I say the hot port is fully opening, you get 122, in reality, there's a little bit bleed by off of that cold port. So it's going to be slightly less than 122. I wanted to throw that out there just to make sure that everybody understands how it actually is working. But for now, I'm just going to stick with the full number. So when the water temperature going to the mixing valve is 122 and the set point is 122, that valve is fully open. And as the temperature out here goes down further, now the temperature going out to the radiant will creep down with it as well. So on a 104 degree day, the water, 104 degree day, that's hot. On a 55 degree day, the water temperature going out to that radiant is probably around 90 degrees. So although I say the thermostatic mixing valve provides control to a set point, once the temperature of the inlet side equals the outlet temperature, the temperature downstream of the mixing valve does change with the outdoor reset if this part of the system is running off of outdoor reset. Okay. So something a little bit I wanted to throw in there about the operation of that thermostatic. Okay. But this becomes a methodology of generating a second water temperature or third. So when I do a thermostatic, it's pros. It's less expensive than electric or motorized valves. It's also less expensive than doing injection pumping. Unlike the other two methodologies, it works without power. And it's temperature operated without external controls. It's just a matter of setting the knob on the top. And also I'm going to add it in here. I don't have it as a bullet, but if the rest of the system's running off of outdoor reset, if the water temperature coming, the hot coming into the thermostatic mixing valve is below the set point, it will drop with the rest of the system. So although it's a fixed temperature valve, you know, there are certain situations where you can get lower temperatures out of it. Okay. The cons or the downsides, it is fixed. So you don't have the ability to do outdoor reset control, which leads to the one on the bottom here, is it provides less energy savings than doing electric or motorized valve because of the fact that it is running in a fixed temperature mode versus modulating the water temperature. Now this leads me on to, that's actually take a quick look here, still no questions coming up. This leads me on to the final version of multiple water temperatures is let's do a motorized mixing valve. So just like the thermostatic, I have 3 ports. I have a hot port here, I have a cold port here, and I have a mixed port, okay? Here's the handle that's on the top of the valve. The motorized unit bolts on top of this, and then it will move the handle based on the boiler control or the control that will run this, this mixing of the valve. So it'll provide outdoor reset control. It will work with the boiler control and also provides outdoor reset water temperature independent of what's happening on the boiler side of things. Okay, so from a piping standpoint, it's piped in just like a thermostatic. A hot connection, a cold connection, and a mixed connection. And the mixing valve is downstream, downstream of the pump. So the pump will draw water through the mixing valve. Now, because it is an electric mixing valve, I will need a strap-on sensor that feeds back to the control. I'll also have to power the mixing valve. And then the mixing valve will also have to have communication with its control to be able to modulate the temperature. Okay. From a startup standpoint, the control does have to be programmed. So it's a little bit more involved when I do a motorized mixing valve. Okay. But what this will allow me to do now is I can take that exact same installation. By the way, I will point out from a drawing standpoint, this valve is not properly oriented, but it fit, I guess it fit with the drawing of, I'm not sure who made the drawing. But now what this allows us to do is I can do outdoor reset here off the boiler for that same high temperature loop. But now I'm doing outdoor reset also here for this part of the building as well. So let's say that was 122 degrees. So it's only 122 degrees here, and it doesn't have to wait. You don't have to wait until the temperature here drops below 122 to start to see the temperature to this part of the heating system to drop. The minute the outside temperature changes, it will modulate the water temperature going out to the side of the system, which in turn drives better comfort, but also it drives a lower return water temperature coming back here, which will help with the boiler efficiency. Okay, so when we start to do mixing valves, typically motorized mixing valves, I have an area of the building, I want to do outdoor reset with a lower water temperature independent of what's happening on the high temperature side. Okay, the other big advantage of this is if I have an indirect and I'm doing non-priority, when the boiler comes up to whatever temperature is required for the indirect and I'm doing non-priority, the mixing valve will maintain temperature out to the heating zone as well. Okay, looks like we have a couple of questions that have come in. So we didn't stop anywhere earlier since there weren't any coming in. So we got here.
We do have a couple questions, Jody. The first one is, for the thermostatic valve example, is there a minimum operating pressure required for both the cold and hot source?
It's actually both questions are pretty much the same question. I'm going to back up quickly for that. Okay. And with this, the one thing when we start to look at doing hydronics, usually when somebody starts to talks about pressure across the mixing valve, they probably have had some sort of experience in the plumbing world. And in the hydronic world, this pump here may only be generating maybe 3, 4, 5 feet of head. So you don't end up with a large pressure difference across here that becomes as much of a problem, okay? And I would have to say also with motorized mixing valve, it never comes up as an issue. With thermostatic, I would say check with the valve manufacturers, but in a hydronic system, I don't think we see pressure differences across pumps that are large enough to cause any kind of pressure differential problem, where because of the pressure differential, you tend to have a higher volume of water coming off of one side than the other. And again, when we start to look at, I'm going to go back to where we were here. We start to looking at adding in here, all of a sudden we start to need more water temperatures. It's just about adding more mixing valve. So here's an application for 3 temperatures. So if I have 180 degrees, I have 140, and I have a 100-degree portion of the building. The highest temperature can run with the boiler. One mixing valve, one motorized mixing valve provides 140. One motorized mixing valve provides 100. And then in this case, with the motorized mixing valves, they then do outdoor reset to change that water temperature. And I get basically 3 outdoor reset temperatures, everything driving down. And by driving it all down, I'm driving down the return water temperature, providing the best economy of the system. Now, a lot of times when we talk about mixing valves, everybody always thinks about multiple mixing valves when I have multiple space heating water temperatures. Something like this, for instance. So here's a drawing that we had put together. And this was somebody's private residence. But again, 3 motorized mixing valves, 3 different areas of the building. And as you can see here, there's quite a different number of zones throughout that building. Okay, but when we start to talk about motorized mixing valves, in the world of commercial buildings, particularly I'll go with apartment buildings, a lot of times we end up with motorized mixing valves that are in buildings, but from a space heating standpoint, you end up with only a single water temperature. And the question always says, I'll put these together and the drawing will go off to somebody and they're like, well, why do I need a motorized mixing valve? I only have a single water temperature. And the answer always is right over here. You're going to have, in your building, you're going to have a fairly high hot water demand, where the hot water demand may occupy 4 hours a day, in an apartment building. Other applications could be even higher, like motels, hotels, and spas. But what this allows us to do with this is it's all about comfort. It's all about driving down return water temperature. So if I didn't have this, whenever the boilers came up to temperature to recover the water heaters, the building would get that exact same temperature. And that temperature is probably going to be somewhere in the 170 to 190 degree Fahrenheit range. But by adding this in here, when the boiler plant and the water heaters come up to temperature to recover the water heaters, the building stays running off of outdoor reset control. So here the water temperature may be 170. Here the water temperature here may only be 100 or 120 degrees. Drives the water temperature down, drives the return water temperature down. So when I look at what's returning to the boiler, it's not based on a single delta T out here, which may only be 30 degrees. It may go out at 100, it may go, let's go out at 120, it may come back at 100, but now I have 100-degree water coming back here, probably mixing with water coming back here as well, in that probably 140-degree range, which, depending on the mix rate, may drive the return water temperature back down to the point where the boilers are condensing. So a lot of times when we have fixed loads, water heating, pool heating, snow melting, we will put the space heating on a mixing valve, even if it's a single temperature, to be able to drive efficiency and comfort in the building. In these kind of applications, mixing valves pay for themselves in a very short period of time because of what this lower temperature return water represents to the efficiency of the boiler. Now, questions about going electrical and motorized versus thermostatic. Okay. And from a crossover standpoint, in buildings, I can approach them both the exact same. I can approach a building with either application. So let's say I have the option of this building that I need 3 different water temperatures. And I'm going to call it water temperatures HC1, HC2, and HC3. So I can run a high water temperature with no mixing valve, a lower water temperature with a mixing valve, and still a 3rd water temperature with a mixing valve as well. Okay. And from an aspect of water temperatures, let's say from a standpoint of requirements, let's say I have these 3 mixing valves, and I can either do it with motorized or I can do it with thermostatic. And in both cases, on the design conditions, HC1 is going to require 61 degrees Celsius. This slide actually was made by one of my coworkers, Mark Norris, up in our Canadian office. And I decided to leave it in Celsius in case somebody from Canada is watching as well. So this part of the building requires 61 degrees Celsius on the design day. This part of the building requires 44 degrees Celsius on the design day. Okay. Over here, the exact same thing, 61 Celsius, 41 Celsius. But let's say we're not on the design day. Let's say the outside temperature is 12 degrees C. Okay. For those of you that are on our side of the border, 12 degrees C, I think that's about 41, somewhere around 41 degrees Fahrenheit. But with motorized mixing valves, let's say HC1, the required water temperature is 38 degrees. Boiler modulates and gives me 38 degrees. With a motorized mixing valve, if the temperature is required is 34 degrees, it also gets 34 degrees. If the temperature here is requiring 68 degrees based on its outdoor reset, it also gets 28 degrees. So right here, all 3 areas of the building get the desired water temperature. And because these water temperatures are lower, that means I'm going to have a lower combined return water temperature going back to the boiler. If I do this with thermostatics, the set point of this is 61, the set point of this is 44C. Okay. Now, if this area of the building is looking for 38 degree water, the boiler will do outdoor reset and deliver that 38 degree water. Okay. Here, based on our schedule, if I was doing outdoor reset, I can heat this area of the building with 34 degree water. Since the supply water is lower than the set point, it doesn't get 61 degree water, it gets 38 degree water. So it does get a lower water temperature, but still it's 4 degrees Celsius higher than it can be. It should be. Over here, the set point was 44. If I was doing outdoor reset, it should be 28. But again, since the temperature here is below the set point, that thermostatic mixing valve is wide open, providing 38 degree water. Again, it could be 28, so you end up with a much higher temperature. The end result is when you start to look at, somebody says, why motorized versus thermostatic? It's about comfort and efficiency. I'm putting out the right water temperature to heat different areas of the building, which helps drive comfort. But additionally, if I'm putting out the right water temperature, I'm getting back the lowest possible return water temperature. It'll help to make that boiler more efficient. So when we start to look at doing thermostatics over electrics, a lot of times comfort and efficiency really are part of the discussion. So I do an electric or a motorized, I can set it up, it can control the system to operate at its various settings. So I can do outdoor reset curve. Additionally, the operation settings are dynamic. Yeah. So if I'm hooked up to a building management system, the building management system through the gateway can change the set point if it's needed. Okay. Excuse me. Because of this changing of the water temperature, it is more efficient than doing a thermostatic because it's always going to drive for the lowest water temperature. And the other thing is internal. If earlier we saw that mixing valve had a handle on it, and then there's an operator here that engages that handle. Okay. And by using this arrangement, if there is a problem with the control of this valve, the handle can be released from the motor, and this can be overridden to a specific manual position. So there is a manual operation built into it. this becomes a nice positive to it, particularly when I'm looking at it versus injection pumping. You know, there is no way to override an injection pump if there's a failure. So this becomes a big positive from that system. The cons, this is going to be more expensive than doing a thermostatic. It is your low temperature solution. It does need electricity to operate, and there is an external control signal to the valve to operate it. So it's a little bit more complex than the thermostatic. Okay? So the differences between the two, to me, thermostatic, if cost is an issue, you know, I'll see projects go thermostatic. Or if the area that they're trying to heat radiantly, for instance, is small that you really can't justify doing a motorized mixing valve, a lot of times that ends up with a thermostatic. Think of a house that the only place they're doing radiant in is to warm the floor in the base and in the bathroom. Something like that probably will go with a thermostatic mixing valve. But when we do the electric or the motorized for bigger applications, you know, there is a definite advantage of going motorized or electric mixing valve over the thermostatic. See if we have any more questions. Nope, no questions at the time.
Jody, we did have one come through the chat if you want to
Okay.
get one. Are there certain applications where you'd recommend injection pump versus modulating control valve?
Unfortunately, I'm biased like anybody else. So from my aspect, I can't really think of any application where the injection pumping has a big advantage over the modulating control valve. You know, for me, there are two different types of approaches to doing it. But when I look at the advantages of doing the motorized mixing valves, you know, I really don't see any real advantages of going with the injection pumping. I mean, you're adding a pump in there that has to operate constantly. You do have to balance the system, and there is really no way to override it if there is a problem. So that tends to push it more in the direction of the motorized mixing valve. Excuse me. Now, the other thing that, final thing we need to talk about when it comes to managing water temperatures is heat pump loops. So commercial, we actually see some residential as well. So when I do a heat pump loop, so I'll have this loop here with various heat pumps throughout the building that can either work in a heating or a cooling methodology. And what we're trying to do is we're trying to maintain a water temperature in that loop for these heat pumps to work against, to use as basically as a sink or a draw from, okay? And so in these, there's always going to be some method of cooling, and then a boiler is going to be placed in there as some method of injecting temperature into the loop itself. Here it's showing these two heating connections here with some device that's going to allow a parallel flow through the boiler. And a lot of times we see this in there as an injection system with a pump injecting water into the loop. Now, the problem we see with a lot of this type of application is the boiler itself runs off of a differential, probably in the neighborhood of at least 10 degrees of operation. So when you look at the water that's being injected into this loop here, where they're trying to maintain a constant water temperature, the boiler, in this kind of thing, the boiler tends to cause a variation in the water temperature. And that variation for the application may not be desirable. So because of that variation and that swing, the question always is there a way to tighten that up? And actually the way to tighten it up is to do something like this. It's really all about, taking what could be just an injection system, bringing water through the boilers, and then injecting that water back into the building heat pump loop. But now let's add in a motorized mixing valve. And not only are we bringing in a motorized mixing valve, we're not going to control the water that's coming out of the mixing valve. We're going to control based on the water temperature out in the loop. And we can go in here and we can specify to the control package how tight we want the differential on that valve. if they want to keep it within plus or minus 1 degree, we can go in there and give us essentially a high and low temperature to keep it within that 1 degree temperature. So here at the boiler, the temperature may swing 10 degrees as the boiler cycles off of, as the boiler maintains temperature. But as it's changing its temperature, the motorized mixing valve is keeping a constant temperature out to the system. Okay. This way here, it gives us a much more defined control over that boiler loop's temperature. And the real key is to add in this motorized mixing valve to make that happen. Okay. Now, the other thing that by doing this, and also by adding in this motorized mixing valve, it now allows us to also better utilize the boilers that are out in this and now into this building. Because here, without that mixing valve, normally we talk about boiler heat pump loops. We're talking about, heat loops that are probably running in the neighborhood of about, I don't know, maybe 80 degrees Fahrenheit as an average. Okay. 80 degrees Fahrenheit coming off of here, there's not a lot of other things you can do with this boiler. But if I put in that motorized mixing valve, all of a sudden, I now can use my boiler plant also to do domestic hot water. So if the requirement here is for 80-degree water, the mixing valve maintains that 80-degree water going out to the building, whether or not the boilers are just providing the right water temperature for the building or the right water temperature for domestic hot water. Because from the aspect of the mixing valve, it doesn't matter if the temperature here is 90 degrees or 190 degrees, the mixing valve will put out 80-degree water temperature. So all of a sudden, by adding this injection with the motorized mixing valve, supplying the building heat pump loop, it now allows domestic hot water or a wide variety of other applications. So here, this building here happened to have it all. Here's domestic hot water. Here's a heat pump loop. Here's a pool heating coming off the same boiler plant. Part of the building is radiantly heated. Here's also part of the building that has a high temperature circuit. So it allows for better utilization of the boiler plant. And the key all of this really is if I didn't have this mixing valve giving me the right control to the water temperature here and finer temperature than I would have had just off of the boiler, this would have required a dedicated boiler plant. But by doing this, it gives me more precise control out to the heat pump loop, and then also allows me to better utilize the boiler plant for other loads within the building itself. So again, from an aspect of doing heat pumps, bringing that motorized mixing valve into the control loop for the boiler heat injection, there's a lot of benefit of doing it this way. So, covered a lot of ground in our hour and a couple of minutes. So here's our learning objectives. So we talked about conditions that lead to multiple water temperatures. We talked about multiple boiler set points. We talked about mixing valves, motorized and thermostatics, and injection pumping. We talked about realistically how many water temperatures are needed for a hydronic system. And finally, we talked about providing a constant temperature to a heat pump loop, regardless of whether it's just standalone or mixed. So, I guess, are there any final questions?
Looks like we don't have any additional questions, Jody.
All right. Well, I'd like to first, before we wrap it up, Doris, I'd like to thank you all for coming. Hope you found the good hour we spent together. And with that, I'm going to hand it over to Miranda.
Great. Thank you, Jody. Just before we close out, just a few reminders. As I stated in the beginning, this has been recorded and will be available on the video library and the YouTube channel in about 2 weeks or so. If you requested a PDH, we will send you the certificate within 5 to 7 business days after you fill out that survey, which will be emailed to you by the end of the day today. If you think of any additional questions, my email is on the screen. You can email us at the Academy and we will make sure that your question does get answered. And we do have a few new presentations coming up. Next week, we have the Viessmann 100, B1HA, B1KA, troubleshooting, faults, OB, and 38. This Thursday, we actually have one on the application and piping for condensing boilers. And then we have Jody back on November 10th and 17th to go over the fundamentals and application of outdoor reset. So feel free to go and register for any of those that you would like to at any time on the website for your country, whether it be the US or Canada. And with that being said, that does conclude today's seminar. Thank you for attending and have a great rest of your day.